Good morning. My name's Carl Stink. I'm with the Office of Advanced Reactor Technologies, and I am the new program manager for our new Advanced Reactor Technologies program within the Office of Nuclear Energy. We have gone through a change this year from last year, which was reflected in our 2015 budget request, and we are awaiting formal approval from Congress for that change. 2 years ago, we combined the high temperature reactor program, formerly the NGNP program, with the Advanced Reactor Concepts program. And with the 2015 budget, we have also combined in the Advanced Small Modular Reactors program together with the ARC program, all into a new program we call Advanced Reactor Technologies. Our program mission is to research and develop advanced technologies to significantly improve efficiency, safety, performance of advanced reactor systems. So as I said, it's a new program in 2015, all rolled together. We broke it out into 5 key program areas: fast reactor technologies, high temperature reactor technologies, advanced reactor generic technologies, advanced reactor licensing, and advanced reactor system studies. That program structure is reflected in the text which you'll be given eventually for focus area RC-2 under NEOP. My program director, Office Director Tom O'Connor. I'm the federal point of contact. Last year it was Brian Robinson. I've taken over this part of our office duties from him. He is focused on another program which you may have read about in the FY15 budget request, the Supercritical Transformational Electricity Production Project, which focuses on supercritical CO2. And our technical point of contact is Dr. Robert Hill at Argonne National Laboratory. He's also on the line. At the end, he'll be available to help answer questions. As I said before, we are in support of NE's mission, and this is explained in our new draft roadmap, which I doubt anyone outside of the department has seen, but it is what we are operating to within the department. R&D objective number 2 is to meet the administration's energy security and climate change goals by developing technologies to support deployment of affordable advanced nuclear reactors. Very similar to the old R&D objective 2 from the 2010 roadmap, slightly changed emphasis on some of the wording there if you want to look it up. R&D objective 3, to optimize energy generation, waste generation, safety, and non-proliferation attributes by developing sustainable nuclear fuel cycles. R&D objective 3 primarily belongs to NE5, the fuel cycle office, but as the office that designs the fast reactors, which go along with many of those fuel management concepts, we work closely with NE5 to make sure that our programs are integrated. So our questions are looking into the following types of things. How can we improve the affordability of nuclear power? As you're all aware, nuclear energy is a very expensive operation or undertaking for utilities. They have to weigh carefully the cost-benefit of what they're going to do before they delve into a nuclear project, especially with currently very new advanced reactor technologies. Introducing something like that into the market is going to be a huge undertaking. So we are looking for every way possible to make this more affordable and more manageable for the commercial utilities. How can we improve the inherent safety of advanced nuclear reactors? Again, for the commercial sector, any new reactor built is going to have to be passively safe and or inherently safe to be permitted by the Nuclear Regulatory Commission. All of the advanced Gen 3 plus characteristics, as well as advanced reactor characteristics of high temperature gas reactors, sodium fast reactors, these are the things that we are looking at and making sure that those are proven and borne out by the theory that is behind them right now. How can we improve proliferation resistance of advanced reactors? This is where we come into looking at fuel cycles, fuel forms, as well as the design of the reactor and the refueling system itself to make sure that it's proliferation resistant. How can we address nuclear waste through advanced fuel cycle options? Once again, this is, as I mentioned, we work closely with the Fuel Cycle Office in NE5 to make sure that the reactors that we are designing are compatible with the fuels that they're working on and the research they're doing in advanced nuclear fuels, and vice versa. They are communicating to us, where they are finding issues and where our reactors can work together with the fuels that they're working on to meet the objectives primarily spelled out in the Blue Ribbon Commission report. Next, how can we expand nuclear technologies into non-traditional nuclear energy markets? Pretty much most process heat applications, which can be done by natural gas currently or by coal, can be done by a high-temperature gas-cooled reactor. So we are looking at how, once that reactor is demonstrated, we can then help industry to market that reactor to non-traditional applications such as desalination, district heating. Hydrogen production is a very big one that we hope to see continued progress in producing non-traditional energy applications. Finally, how can we increase the performance and efficiency of advanced nuclear plants through new materials, advanced systems, and components? This is where we try to think outside of the box regarding those areas such as materials, systems, and components. But I want to stress we are not looking for new reactor system concepts as a whole. Okay? Our office is not looking for a wood-moderated reactor, to say something really silly. But we would like to see within the concepts that we're looking at high-temperature gas-cooled reactors, sodium-cooled fast reactors, and fluoride salt-cooled high-temperature reactors. What are the materials, systems, and components that can make them work more efficiently, better performance, and more desirable? So in the work scope description, which you will receive, you'll see the following items. We want them, these reactors, to reach their potential through components and technologies which display the following. Improved design approaches, such as compact configurations to reduce cost and improve component performance. Obviously, if you design something that is smaller, more compact, requires less steel, requires less concrete, requires less exotic metals, that is going to be cheaper. Also, it's going to have a smaller footprint if it's a smaller plant as well. Moving from, for example, a large steam turbine bay that takes up an entire turbine bay in a commercial nuclear power plant today to a supercritical CO2 turbine of the same size, which would fit easily inside this room, probably inside half of this room because of the small size of the small size and power efficiency of a supercritical CO2 turbine. We're also looking at in-service inspection technologies and techniques for innovative reliability and maintenance applications. As you can imagine, when we're working with coolants other than water, which is you're able to see through it, when we work with liquid sodium or sometime in the future lead, or when we have graphite for a moderator in a high-temperature gas reactor. You can't see that. So what in-service inspection is needed in the first place and how to conduct it and what tools do we need for that is another area to look at. Compact heat exchangers or innovative steam generator designs. I've alluded to this already, but that is an area that we're also doing research in and have projects with some universities already. Advanced reactor technology solutions for hybrid energy systems. Clean baseload power sources and intermittent renewables integrated on the grid. This is possibly the one that I am most excited about and involved with today because we have just had a workshop at Idaho regarding this topic, the need for when you have mandates for renewable energy to be placed onto the grid, what happens to your baseline grid power sources? There are examples in California already where, because of their state rules for preferentially putting renewables onto the grid first, it pushes things like nuclear and coal off of the grid during the day. Around 5 in the afternoon, those sources have to be available and ready to come back online when the sun goes down. This creates problems for operability of nuclear power plants, which have been designed over the past 20 years and perfected in their operations over the past 20 to 30 years to run 24/7, 100% power, 99% capacity factor. So being told you have to shut down and start up once a day may be good for a naval nuclear power plant that I worked on, but it was not good for the current civilian nuclear power plants. So looking at that area, some of the areas where you might be able to have inputs is on technical and economic evaluation of some of the solutions that are being proposed for these hybrid systems. Could also provide gap analysis for preferred nuclear hydrogen architectures. So once again, we're starting to think towards nuclear hydrogen and hybrid energy, including hydrogen as a storage medium for energy. These are areas that we do not have direct programmatic funding for, so university funding in those areas would be ideal and perfect. I should have put it into my presentation. Just realized that the main point of contact is Shannon Bragg-Sitton at the Idaho National Laboratory and Richard Boardman. And so we'll make arrangements for them to be able to talk about the specifics that could be used on those studies. Other system studies that are in our suite are also general economic analyses of any type of advanced nuclear reactor system and other studies such as that, which have been done in the past. As always, highlighted in red, experimental demonstration and validation is encouraged. The things that you can get your grad students to do experimentally really show that this stuff really works, and so that's great. One final note before I leave this slide, as I said in the beginning, no new concepts. We want new components, new ways to use existing components within the suite of systems that we're looking at right now. The fast reactors, which is our focus is on sodium-cooled fast reactor, and then high-temperature reactors, both gas-cooled and fluoride cell-cooled. Just some examples of our awarded NEOPs for the past few years are shown on this slide. I'll let you read those for yourself, but it gives you an idea of the type of ultrasonic techniques for in-service inspection or for maintenance monitoring, thermoelectric driven sustainable sensing actuation systems, integrated reactor containment condensation models, experimental validation, new mechanistic models for creep, fatigue, crack growth interactions for advanced high-temperature reactor components. A lot of modeling, which is great. If you can match up that modeling somehow with some experimental validation, even better. And I'm available now for any questions.
Okay, we'll start with our first question. With regards to gas-cooled reactor research, there appears to be some overlap between RC-1 and RC-2. Could you clarify the distinction? And if a PI is submitting a proposal on gas reactors, how could they be sure that they are submitting to the correct work scope area?
Good question. Probably something we should have thought about more ourselves, and I think we run up against it during our review process, where we will get proposals that will come in that are misbinned, and we do have a binning process where we try to resolve that. Let me first say that your pre-proposal will get reviewed one way or another. I think traditional methods and computational methods analyses, safety methods analyses are what go into RC1. RC2 is more focused on component performance, and in the area of system studies, instead of doing modeling of a specific reactor safety performance or a core neutronics performance, then we're more looking for a integrated system analysis of, say, a reactor along with a hydrogen production system, along with a grid application. That would be a system study, as we refer to it. Bob, can you add anything?
Yeah, you covered it well, Carl. RC1 is more focused on modeling and simulation focused proposals, whereas RC2 is more technology focused.
What do you mean by generic technologies? Could you please elaborate?
I should have gone into that, yes. Generic technologies are things that could apply to several different reactor concepts, both fast or thermal, or somewhere fuzzy across the line. So that is where materials goes. Some of our materials research is both for high temperature reactors as well as fast reactors. Doesn't happen often, but sometimes. But the materials work is in that bin. The energy conversion work, which can apply to both a high temperature reactor or a fast reactor. You can hang a supercritical CO2 turbo machinery system off of either type of reactor. So that's within the generic systems. And there's a third key one I'm blanking on right now.
Instrumentation and controls, Carl.
Okay, thank you, sir. Instrumentation and controls is the third key area within generic systems. So these would be instrumentation and control systems for any nuclear application, focusing, however, on advanced nuclear reactors. If it's something that's in the light water community, we probably will not be supporting it. We'll refer your idea to industry for them to develop it, the light water industry.
In previous webinar sessions, the MSR and thorium-based fuels were deemed not relevant for this FY15 FOA. Are these also irrelevant for the economic analyses for advanced reactor technologies?
Insofar as molten salt reactor applications are dually applicable to fluoride cooled high temperature reactors, molten salt technologies could be considered. Thorium applications, however, is currently the department's, it's not an area the department is currently working on at this time.
As a reminder, what was stated in yesterday's webinar session was that if there is thorium-based project or something that does not fit into the current program supporting work scopes, those proposals are being taken in MS NEAT 1, which is a mission supporting area that focuses on other research that isn't being supported by the program supporting section.
Thanks.
Next question. What about proposals that address technologies or applications that are also relevant to water-cooled reactors?
Good question. If it is dual purpose, but the primary application will be for an advanced reactor system, or in case it's something that we really want for advanced reactor systems, but the light water community currently is not interested in paying for it for their own application, if they feel they don't need it, then we will consider it as something that we could put into future advanced reactor designs. We are looking for anything to make the overall reactor system better, including things that could make a light water system better, but they're just not paying for it right now.
So the term advanced means only non-cooled or non-water cooled reactors.
That is correct. And that hopefully is clear from our budget request, and when you read our mission statement is that we're working on advanced non-light water concepts, which are done under the Office of Light Water Reactor Sustainability here in DOE to some extent, and the to another small extent, the licensing technical support program for small modular reactors.